Hello, I am Giorgio Sterticni, and today I will present you a dataset reduction framework for intelligent fault detection in IoT-based cyber-physical systems using machine learning techniques. Before I start, I would like to thank European Union and Cyprus government as this work is funded under the GeoCOE Horizon Teaming Project. This work is done by me and my supervisor, Professor Maria Michail. We both work at the Electrical and Computer Engineering Department and at Chios Research Innovation Center of Excellence at the University of Cyprus. This is a small overview of today's presentation. First of all, I will introduce you to today's topic and also we'll see the motivation behind our work. Then I will give you the theoretical formulation of the problem under consideration, followed by the framework that we propose. Given the framework, we will see how this works in two experimentally evaluated datasets, and we'll conclude this presentation by giving some concluding remarks and the directions of the future work. Cyber-physical systems are the integration between physical processes and computing devices through the use of digital communication channels. Internet of Things-based cyber-physical systems are characterized by the fact that IoT devices are located in the core of the system and they are in a constant communication that aims to provide a better monitor and control. This constant communication now enables the generation of a large amount of data. IoT devices operation in these systems is crucial, and thus any abnormality in these devices can also lead the system to misbehavior. IoT devices now, like any other physical device, are also susceptible to component faults that lead the whole system to abnormal behavior. Thus, the detection of such abnormalities in the system is important for the operation of the whole system. The use of machine learning models that take advantage of the large amount of data that are generated for the fault detection procedure under the intelligent fault detection term becomes nowadays important. In our previous work, we studied the problem of differentiating between faults and attacks that affect the normal operation of IoT-based cyber-physical systems using machine learning classification algorithms. The detection of the abnormality, while also then distinguishing between fault or attack, strongly depends on the training process of the classification algorithms. This training process requires time and also computational resources. At the same time, the operation of such detectors is real-time, which add some important time constraints to the training of such models. Thus, the reduction of the training time as much as possible without violating the performance of the algorithm is important. Dataset reduction schemes in machine learning are divided into two approaches, feature-based and instance-based. Both approaches aim to reduce the volume of the original dataset while also the computational resources required for the training process while preserving the performance of the trained algorithms. Feature-based schemes aim to perform a dimensional reduction in the feature space of all the instances. Instance-based schemes now aim to identify a subset of the initial dataset that is able to achieve the same goal as the initial dataset. As we already said, the real-time detection of the abnormalities in IoT-based cyber-physical system is important, while also the reduction of the processing time as much as possible. Thus, in our work, we aim to provide a machine learning-based framework for the instance-based dataset reduction with a focus on datasets used for the intelligent fault detection task in IoT-based cyber-physical systems. So, our problem is described as follows. We begin by having an initial dataset given by TR, which is consisted of instances from system's normal operation under the normal class given by the capital N, and a set of faulty behaviors under a set of faulty classes given from F1 to Fn. Then we have a set of M classification algorithms in the set of ALG that are trained using the TR for detecting faults in the system. Each algorithm AI achieves an accuracy over TR given by AC AI TR, and also all the algorithms have a mean accuracy of AC MU over TR. What we aim to find is a reduced dataset, dr dash, which will be consisted of instances from the normal class and the subset of the faulty classes up to n prime, which n prime will be less than n, such that given this reduced dataset TR dash as part of the training process of all the classification algorithms in ALG, their accuracy is improved, and this also consequently leads to the improvement of the mean accuracy. The procedure that allows us to go from TR to TR dash will be based on a machine learning based framework for instance-based dataset reduction. Before we discuss the proposed framework, it's important to define here the dominant operator. This is a key definition that will allow us to derive the reductions between two datasets. As we already said, our initial dataset is given by the TR. We also introduce here this set of F train, which is consisted of the set of 40 classes that are used as part of the training. Dataset TWJ is the dataset TR with the difference that the instances of a single faulty class, this of Fj, are not used as part of the training. TWJ is an example of a reduced dataset TR dash, as we said in the problem formulation, as this does not contain the instances of a faulty class Fj. Dominant operator now is defined over the set of the classification algorithms ALG, and it's such that given these two datasets, TR and TWJ, the set of the classification algorithms in the ALG and their accuracies over the training with TR and TWJ, the F-train set of 40 classes without the use of Fj and Fj class is such that the set of 40 classes from F-train dominant using the set of the classification algorithms, the Fj class, if and only if the accuracy that is achieved using as part of the training the reduced dataset TWJ over the TR is improved, while also the mean accuracy is also improved. As we can see in the Venn diagram, the faulty covered area without the use of these Fj instances is such that can also cover the faulty area that is covered from this faulty class. This is a clue that will allow us to remove instances of this Fj class and derive a reduced dataset. So, here is our proposed framework. Our framework, which is based on machine learning and is used for instance-based dataset reduction, is composed of 3 steps. In step 1, we perform a feature ranking for every faulty class. In that step, we generate the MSF FI sets for all the faulty classes, which capture the most significant features of each faulty class that are used as part of the fault detection procedure. The ranking scheme we used for this step is the information gain. Having these MSFI sets, we extract in the second step the possible dominant cases. This is done by generating CFIJ sets that capture the common significant features among two classes Fi and Fj. A possible dominant case is derived if and only if these two classes Fi and Fj share half of their most significant features. In order to derive the dominant operation that will allow us to reduce the initial dataset to a possible reduced dataset, we need to experimentally evaluate all possible dominant cases using the set of the machine learning algorithms in ALG. For that reason, in step 3, we generate the TWI and TWJ reduced dataset by removing the instances of FI and FJ class respectively, and we compute the accuracies using these two datasets as the dataset of the training process. Let's see now how our framework works in two different datasets that are used for the intelligent fault detection in IoT-based cyber-physical systems. The first dataset is derived from our previous work where we examined 40 scenarios in an energy-aware smart home system. The dataset that is used in this experiment is derived from a simulation environment where peripheral devices are connected and communicating with a central coordinating device every minute. The faults that were simulated affect the communication of a single peripheral node and the central coordinator, and this has an impact of losing the communication between the peripheral node and the central coordinator. The three classes of faults that were simulated are low energy failure, routing failure, and packet drop failure. Dataset now contains instances of the normal operation of the system where no fault appears, instances from the low energy failure, routing failure, and packet drop failure. The amount of instances per class is given in the table in the left side. The experimental set of algorithms ALG that were used as part of the intelligent fault detection were knife-based, J48, multi-layer perceptron, and multinomial logistic regression. The features that describe the instances in this dataset are mainly based on traffic, delays, and throughput characteristics. This is how our framework steps are executed using this dataset. As we said in the first step, we perform this features ranking for the 340 classes. These are the 9 most significant features for the 340 classes F1, F2, and F3. As we can observe, a possible dominant relation exists in all the 340 classes, and thus we can derive 3 possible dominant cases of F1 and F2, F1 and F3, and F2 and F3. In the third step, as we already said, we need to experimentally evaluate all the possible dominant cases using the set of the machine learning algorithms in ALG. Those are knife-based, J48, multi-layer perceptron, and multinomial logistic regression. The 3 datasets that are used as part of the training is the initial tier dataset consisted of the normal class, F1 class, F2 class, and F3 class, while also the reduced dataset TW1 and TW2 where we remove the instances of the faulty class F1 and F2 respectively. As we can observe, the accuracy using the TW1 as the dataset of the training increases in all the fault algorithms. Thus, we can define the dominant operator using the set of the faulty classes that were used as part of the training in the TW1. These are the F2 and F3, which are dominant using all the 4 algorithms, the F1 class. As a result, the tier dataset can be reduced to the DR-DAS dataset by removing the F1 instances from the dataset. The mean accuracy is improved from 95.8 to 100%, and thus we have an accuracy improvement of 4.2 and a dataset reduction on a 20%. The second case, where we have the faulty classes of F1 and F3, confirms our finding from F1 as we observe that the TW1 dataset used as part of the training achieves an accuracy improvement in all the fault algorithms and in the mean accuracy of 4.2. Thus, TW1 can be used as the training dataset, which is also a reduced dataset from TR. TW3 doesn't show any improvement in all the classification algorithms and thus cannot be used as a reduced dataset. Finally, in the last case, where we have the faulty class F2 and F3, we observe that the accuracy is not improved in all the classification algorithms, and thus no dominant relation can be extracted using these two reduced datasets. Our second experimentally evaluated dataset is derived from Mississippi State University and Oak Ridge National Laboratory testbed, where it models an industrial control system of a power generation using two generators and a control room. In this dataset, we consider the normal class operation while also 6 different faulty scenarios that all model the single line to ground fault. What makes these scenarios to be different is the area where the fault appears, while also in which of the two transmission generation lines. We have 3 faults for each generation line, and those are separated in the area where the fault appears, with the 10 to 19 denoting the left side, 20 to 79 the middle line, and 80 to 90 the right side of the line. Thus, in total, we have 6 different faulty classes with the number of instances per class given in the table of the slide. Now, the experimental set of the classification algorithms we used remains the same as the previous experimental evaluation, where we have naive Bayes, J48, multi-layer perceptron, and multinomial logistic regression. These dataset instances are described under physical-based features that give the voltage, angle, magnitude, the current, angle, and magnitude, and also some other frequency characteristics. Now, we have to see how our proposed framework steps are executed using these datasets. As we have before, in the first step, we have the most significant features given in the sets of the MSF FI for all the 6 faulty classes. As we can observe, the classes that share half and above of their most significant features, and this leads also to the derive of the possible dominant relation cases, are pairs of F1 and F4 faulty classes, F3 and F5, and F4 and F6. Now, we need to experimentally evaluate the possible dominant cases derived from the previous steps using the set of the machine learning algorithms of ALG. The datasets we consider in this first case, where we have faulty class F1 and F4, are the TR, which consisted of all the faulty classes and the normal class, and also the reduced TW1 and TW4 datasets that are derived after the removal of F1 and F4 instances from the initial dataset TR. What we can observe is that using the TW4 dataset as the training dataset, accuracy is improved in all the fault classification algorithms. Thus, the rest of the faults that are used as part of the training in this dataset of TW4 dominant using all the set of the classification algorithm ALG, the F4 class. Thus, TR dataset can be reduced to TR dash by removing these F4 instances. The mean accuracy is improved from 78.065 to 9046. This is an average accuracy improvement of 12.4 and a dataset reduction of 15.51%. In the second case, where we have faulty classes F3 and F5, we generate again the reduced dataset TW3 and TW5 by removing the instances of F3 and F5, but as we can observe, the accuracy is not improved in all the classification algorithms for at least one of the datasets. Thus, no dominant relation can be extracted, as none of the cases shows an accuracy improvement on per algorithm and also on an average based. Finally, in the third case, where we have the faulty classes of F4 and F6, we confirm our findings from the first case, where the TW4 reduced dataset by removing the instances of F4 achieves an accuracy improvement in all the classification algorithms and thus an average improvement. TW6 does not achieve an accuracy improvement in all the classification algorithms. Thus, by reducing the TR dataset into the TR dash with the removal of the F4 instances, accuracy is improved in terms of its mean from 78.065 to 90.46. This is an average accuracy improvement of 12.4 and a dataset reduction of 15.51%. As for the conclusion, in this work, we achieved to provide a generic framework using machine learning techniques for the instance-based dataset reduction of datasets that are used in the intelligent fault detection of IoT-based cyber-physical systems. We, furthermore, experimentally evaluate our framework using two different datasets, where in both of them we achieved to reduce the initial volume of the dataset and decrease the performance of the classification algorithms as per case and also on average. As for the future work now, we aim to extend the dominant operator so that it can also dominate over more than a single class. This will also allow us to remove more classes in the reduced dataset, while also to extend the framework so that it can also deal with other sources of abnormality, such as attacks and datasets that are used in intrusion detection systems. Thank you very much for your attention.